The universe is being pulled apart. Something is stretching it, slowly. That's the big rip. It's an idea where dark energy, the thing that's making the universe expand, it turns against everything. It could tear everything apart, galaxies first, then stars, then planets, then the atoms in your hands. It's a systematic destruction. Astronomers were stunned when they found the universe was speeding up. They didn't expect that, and if dark energy is a certain kind, if it's what they call phantom energy, then given enough time, it could do this. It could unravel the fabric of space itself. The end of everything might be written into that fabric. That light had a message, and it broke what everyone thought they knew. In the late 90s, two groups of astronomers were looking at distant supernovae. Using these exploding stars as markers, they expected to see the universe's expansion slowing down, pulled back by all the gravity from all the matter. But the light from these old explosions said something else. It said the universe was speeding up. It wasn't just expanding, it was flying apart faster and faster. This came from the Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Adam Rees. It sent shockwaves through science. It was so unexpected, so against everything they knew, that the researchers spent months checking and rechecking. They were sure there was a mistake. There was no mistake. The universe was accelerating, and that meant something invisible was at work, something powerful, pushing everything apart. They called it dark energy. And they calculated it made up 68% of everything. To understand it, scientists went back to an old idea, one Albert Einstein had proposed. He later called it his greatest blunder, the cosmological constant. In his equations for general relativity, he'd put in this mathematical factor, a repulsive energy built into empty space itself. To keep the universe still, he threw it out when Edwin Hubble proved the universe was expanding. Now, decades later, it came back as the main candidate for dark energy. A gentle, relentless pressure woven into the vacuum. That was the pivotal clue. The moment everything turned over, the dominant force in our universe isn't gravity pulling things together. It's dark energy pushing them apart, and if that energy isn't the gentle, constant Einstein thought, if its push can get stronger over time, then the story of our cosmos takes a turn. A terrifying one. The simplest model we have is the cosmological constant. It's a property of space itself. Even a perfect vacuum, a completely empty cube of nothing, would still have this faint, repulsive energy. It doesn't change, it doesn't weaken. It's just a constant, gentle push woven into reality. In that model, dark energy has a specific mathematical signature, a value scientists call W, which equals -1. That's the baseline, the steady hum of the universe's engine. But many scientists wonder if it's really that simple. Could dark energy be something more dynamic, something that evolves? That idea is called quintessence. Imagine it not as a constant property of space, but as a kind of energy field that fills it, a field that can change its strength over time. Its value, its W, could be different. To measure this number, astronomers don't just look at one thing. They combine evidence. They study light from distant supernova. They look at the afterglow of the Big Bang frozen in the cosmic microwave background, and they study the faint echoes of ancient sound waves imprinted in the distribution of galaxies, called baryon acoustic oscillations. Each piece of data helps pin down the true nature of W, and here's where the story takes an unsettling turn. What if the measurements one day point to a value for W that is not just -1, but something less? Something like -1.1 or even lower. That's the realm of phantom energy. In that scenario, the repulsive force doesn't just stay constant. It grows stronger as the universe expands. The push becomes a shove, then a violent heave. The expansion rate wouldn't just continue. it would accelerate without limit, increasing toward infinity. That phantom scenario is the direct mathematical pathway to an end so absolute, it defies our understanding of existence. It's the precursor to the Big Rip. Phantom energy changes the fate of the cosmos. In 2003, a team of cosmologists, Robert Caldwell, Mark Kamiankowski, Nevin Weinberg, they followed the math of this idea. They followed it to its logical conclusion, and they formalized a hypothesis so stark it needed a name that matched its violence. They called it the Big Rip. The theory describes a cosmic countdown. The scale of the universe doesn't just grow large, it becomes mathematically infinite, and it does this within a finite amount of time. This isn't about things getting very far apart. It's about the fundamental rules of physics breaking down at a specific, calculable moment. The engine behind it is phantom energy's sinister property. As the universe expands, the density of this dark energy doesn't thin out. It doesn't stay constant. It actually increases. More space creates more repulsive force, which creates more space even faster. It's a runaway feedback loop of creation. The Hubble parameter, which measures the expansion rate, it doesn't just rise. It races toward infinity. We can put a timeline to this unraveling. It wouldn't be a chaotic explosion. It would be a systematic dissolution. A hierarchical dissolution working in reverse order of gravitational binding. The clock starts ticking long before the final moment. First to go would be the largest, most loosely bound structures. Galaxy clusters, those immense cities of stars held together by gravity, they'd be the first to drift apart, to become isolated islands. Next, the galaxies themselves would be shredded. The stars within a galaxy like our Milky Way would be flung away from each other. They'd become lonely voyagers in an ever-darkening void. Then, the grip of individual solar systems would fail. Planets would be torn from their suns, cast adrift into the freezing black. As the phantom force intensifies, it overcomes the gravity holding planets together. A world like Earth would simply come apart. Its mountains, its oceans, its crust pulled into space. Finally, in the last instance, the forces that bind matter itself would be overwhelmed. Molecules would be ripped into atoms. Atoms would be shredded as the electromagnetic force fails. Electrons torn from nuclei, and in the final fraction of a second, even atomic nuclei would be torn apart. Protons and neutrons scattered by a force greater than the strong nuclear force. The universe would end not with a collapse, but with a silent, ultimate dissolution. Into a thin, cold mist of fundamental particles, too far apart to ever interact again. This vision turns an abstract equation into a sequence, a step-by-step guide to the end of everything. The universe we see now is this structure, the cosmic web. It's made of these huge filaments of dark matter, and along them you have galaxies like lights on a string. And those filaments connect at these dense nodes where thousands of galaxies are gathered in clusters, all of it held together by gravity. It's the biggest thing we know. And it would be the first thing to go. The Big Rip, the start of it, isn't a sudden thing. It's a slow unraveling. It starts at the very largest scales. As phantom energy grows, its repulsive force starts to work against gravity. On this huge scale, the cosmological horizon, the distance where things can still affect each other, it starts to shrink. The universe's sphere of influence gets smaller, even while space itself is getting bigger. The first connections to break are between the superclusters. These massive groups of galaxy clusters, right now they're drifting toward each other slowly, but in this scenario they start moving apart instead. Faster and faster, their gravitational ties stretched over hundreds of millions of years, they finally snap. Each supercluster becomes an island, alone in this growing sea of darkness. Then it moves inward to a single galaxy cluster like our local group, the Milky Way and Andromeda. Right now, Andromeda is headed for us, pulled by gravity. But with phantom energy, that changes. The accelerating expansion would eventually overcome even that local pull. The galaxies in the cluster, they'd see their neighbors not as partners coming closer, but as ghosts fading away. Their light would stretch redshift longer and longer wavelengths until it's invisible, carried off by the space stretching between them. This is the point cosmologists note. The transition, the moment the large-scale structure of the universe stops being gravitationally bound, it becomes entirely dominated by the phantom force. The cosmic web, built over 13 billion years by gravity, it starts to dissolve. Its filaments stretch and thin out until they're gone. The nodes of light, they just drift apart. Into isolation, this first stage is a prelude, a profound loneliness. It's the end of the universe as a connected structure. No new light from distant superclusters will ever reach an observer in one of these fading clusters. The sky, which once held this map of everything, it grows dark, empty. The architecture is coming down. The demolition starts from the top, and then the phantom force turns its attention to things closer together. To the galaxies themselves, to the stars. That's when the dissolution becomes personal. Our own galaxy would start to feel that strain long before anything actually came apart. It's not a sudden blow. It's a pressure that just keeps building right in the fabric of space itself. And the first things to go would be the biggest gravitational bonds we know, the ones in our local neighborhood. The local group, that's this family of galaxies, more than 50 of them with the two big spirals, the Milky Way and Andromeda. We're on a collision course right now. Andromeda is coming toward us, drawn by the gravity between our two galaxies. That was the future once. They'd merge over billions of years, but with phantom energy, that future gets erased. The phantom force grows until it's stronger than the pull between the galaxies. So Andromeda wouldn't keep approaching. It would slow down, then stop. Then it would start moving away. The whole local group's gravitational glue would dissolve. Every galaxy, the big spirals and the little dwarf ones, they'd all drift apart on their own paths, pulled by the stretching space. They'd become isolated islands, and to anyone still inside, their lights would grow dimmer and redder until they finally vanished over the horizon. You'd see signs of this long before the separation finished, billions of years before, written in the light of the galaxies. Their shapes would start to distort. Those spiral arms, held together by the star's rotation and gravity, they'd get pulled and stretched by phantom energy's tidal forces. They wouldn't be neat pinwheels anymore. They'd look warped, like a reflection in a funhouse mirror. The outermost stars, the ones in the halo that are only loosely bound, they'd be stripped away first. A galaxy would slowly lose that faint outer glow. Its boundaries would get sharper as the most distant stars were pulled into the void. It's a slow-motion unraveling over eons. The galaxy's structure, its identity, taken apart by an outside force. The result is a deep loneliness. Each galaxy becomes a ship with its lights on, sailing into a darker and wider ocean. No new stars would be born from galaxy collisions. That fuel is gone. Each island universe is left with only the stars it already has, burning through their lives alone. The cosmic community, built over billions of years of gravity, would stop existing. The universe goes from a web of connected structures to just scattered points of light, each one watching the others fade away. And as the phantom force keeps strengthening, it turns inward to the galaxy's own heart. The bonds holding stars around their central black holes, they'd be next. The phantom force tears apart the cosmic web, and then it focuses on the galaxies themselves. In the Milky Way, a tension begins. For billions of years, the galaxy was a balance. Gravity pulling in and the momentum of stars in orbit pushing out. That balance breaks. The phantom energy's repulsive force gets so strong it acts like a tidal force, stretching the galaxy from the outside. The stars on the very edges feel it first. The galactic halo, that sphere of ancient stars and clusters around the main disk, it just evaporates. Those stars are on tenuous leashes, and they're plucked away one by one. Their trajectories bend away from the center, flung into the void. Their light redshifts into blackness, vanishing from the sky. Then the spiral arms start to distort. They're not solid, they're density waves, like traffic jams in the flow of stars. The phantom force stretches these waves, pulls the stars apart. The pinwheel shape warps. The arms become long streams, then they dissolve. The galactic disk, that flat plane, it buckles and tears under the strain. From inside, the night sky transforms. The constellations are the first to go. Orion, the Big Dipper, they're not bound together. They're just a line of sight from here. As phantom energy pulls each star onto a different path, these patterns stretch. They smear across the sky. It becomes a chaotic tapestry of streaking lights, each star moving on its own until no shape is left. You're watching the landmarks of the cosmos, the constants of all human history, being erased. The dissolution moves inward, the central bulge, that dense crowd of older stars, and the supermassive black hole at the heart, Sagittarius A, they hold on the longest. Their gravitational grip is immense, but in this scenario, no force is safe. Even this anchor feels the strain. The stars closest to the black hole are the last to go, ripped from their orbits in a violent spiral outward as the phantom tide overcomes even that extreme gravity. The Milky Way took over 13 billion years to form. It's taken apart in a much shorter final chapter. Its stars become isolated voyagers, carrying the frozen remnants of any planets. And for our own solar system, adrift in all this, the clock is ticking down to a more intimate catastrophe. The Sun's gravity has held Earth for 4.5 billion years. That's going to end because phantom energy's density keeps increasing. Its repulsive force will eventually match the Sun's pull, and the balance of our orbit, that rhythm of seasons and millennia, it becomes unstable. We can even estimate when. In the Big Rip scenario, with those specific phantom energy conditions, Earth would become unbound from the Sun about 3 months before the final rip. 3 months out, it starts gradually. The orbit doesn't just break, it widens. Earth's path around the Sun, that ellipse, it begins to stretch. Each year gets a little longer. The planet drifts outward, spiraling away. The other planets follow, each at its own pace. Their clockwork unravels. Mercury and Venus, the inner worlds, they might hold on a bit longer. But not for long. The giant planets Jupiter and Saturn, with their huge gravitational influence, they'd be the last to let go, but even their hold breaks. Then consider the smaller objects. The asteroid belt, that relic from the system's formation, it would scatter instantly. The phantom force overcomes the weak gravity holding those rocks together. They get sent on lonely paths into the dark. The distant Kuiper belt, home to Pluto, and the Oort cloud farther out, the source of comets, they just dissipate. Those objects were barely bound to begin with. They'd be among the first cast adrift. From the surface of a drifting Earth, the sky tells the story. The Sun, our constant companion, it starts to shrink. Day by day, it grows smaller, a brilliant coin dwindling to a distant point. Its light, already stretched by the expansion of space, reddens, a deep, bloody crimson. The warmth fades, global temperatures plummet in weeks, photosynthesis stops, the blue sky bleaches to black, stars become visible during the day, though they too are streaking and fading. And finally, the Sun winks out, not with an explosion, it fades to black. It becomes just another star in the void, then not even that. Perpetual night and deep cold claim the planet. Planetary scientists note the silence of it. There's no sound in the vacuum, no catastrophic collision, just the silent severing of a fundamental bond. Earth and every other planet becomes a rogue world, a dark, frozen ball of rock and ice tumbling through an emptiness growing more intense by the hour. Its journey is lonely and tragically brief because the phantom force isn't done. It shattered the solar system, but its true goal is the very matter the planets are made of. The dissolution is about to become intimate, moving from celestial mechanics to the fabric of matter itself. The end isn't a quiet freeze, it's a violent unmaking. Earth is a dark rogue world now, drifting where space itself is stretching faster and faster. That creates a tidal force, but not from a star. It's from the expansion of the universe. A phantom energy pulling from all sides. It's a tensile stress, like pulling a rubber band from both ends. What holds the planet together is its own gravity, the chemical bonds in the rock. That's the rubber band's elasticity, but the phantom force keeps intensifying. The stress increases until it exceeds the planet's self-gravity. That point where a body is torn apart by tides is called the Roche limit. Usually that's for a moon getting too close to its planet. Here, the planet itself hits a Roche limit with the expanding universe. For a rocky world, the end is a global cataclysm. Long before the final snap, the stresses start. They trigger planet-wide tectonic upheaval. The phantom force pulls on the crust, amplifying everything that drives earthquakes and volcanoes. The surface becomes one continuous seismic event. Mountain ranges crumble as the bedrock stretches. The molten core, under new pressures, finds violent release. Supervolcanoes erupt everywhere. The crust splits open along continental seams. Glowing rivers of magma light the perpetual night. The atmosphere, already freezing and thin, gets stripped away by the outgassing and the relentless pull. Then comes the fragmentation. The planet doesn't explode, it's pulled apart. The tensile stress wins. The rock can't hold together against the stretching of space. The sphere distorts, it elongates like taffy. It fractures at its weakest points, breaking into continental-sized chunks. Then those chunks break again, into smaller pieces, until all that's left is a cloud of dust and rubble, each piece on its own trajectory into the void. For a gas giant like Jupiter, it's different. But no less absolute, no solid surface. It would be a gradual, monstrous evaporation. The phantom tidal force pulls the outer layers of atmosphere away first. Like a cosmic wind stripping a cloud, the immense pressure and heat inside burst forth as the planet's structure fails. The iconic bands, the great red spot, they smear and distort. Then stream away into space. The core, a ball of metallic hydrogen and rock, might hold a moment longer before it too is dissected. Jupiter wouldn't so much break as puff away into a dissipating nebula, its material scattered across light years. This stage shows a chilling principle. In the Big Rip, no amount of mass is safe. A planet's gravity, what shaped it and held its atmosphere for eons, becomes irrelevant. The force dismantling everything operates deeper. It attacks the bonds of space-time that let matter cohere in the first place. It reduces worlds, these cradles of potential life and history, to anonymous debris. And once the planets are gone, the phantom energy turns to the last bonds. The smallest ones, the most fundamental. The star is the last source of warmth, the final one in all that cold and dark. For billions of years, a star like our sun exists because of a balance. Two forces, there's the gravity, the crushing weight of all that mass pulling inward, and then there's the outward pressure that comes from the nuclear fusion in its core. The push against the pull, that equilibrium is what a star is, but phantom energy, that's a new pressure, an external one, a repulsive force pulling from the outside. And as that force grows, it starts to help the star's own internal pressure. It works against the gravity, so the balance tips. The star doesn't collapse under its own weight. Instead, it swells, it inflates uncontrollably. For a star like the sun, already alone out there, the end is a violent inflation. The phantom force lowers the effective gravity. The force that was holding the star together, the outer layers, they're not bound as tightly anymore, so they expand. but this isn't like the red giant phase, that slow puffing out. This is rapid, a catastrophic decompression. The star's envelope balloons outward. It cools as it expands. The core, where fusion was happening, gets exposed and it starts to cool. In a matter of months, maybe just weeks before the final rip, the star dissipates. Its plasma gets pulled into a thin, expanding cloud. Its light fades. From a bright point to a dim, red smear, and then to nothing, the nuclear furnace is snuffed out, not because it ran out of fuel, but because the universe itself undid the knot that contained it. But stars leave behind corpses, remnants of incredible density, and even these aren't safe. Take a white dwarf. It's a sphere of degenerate matter, a star's mass crushed into a volume the size of Earth. It's held up by quantum mechanical pressure, a force so strong it defies any further collapse. Phantom energy, growing without limit, could theoretically overcome even that. The white dwarf would be stretched, pulled apart. Its crystalline carbon and oxygen structure would be shattered. Then there are neutron stars, the densest objects we know, short of black holes. A teaspoon of that material weighs as much as a mountain. They're like atomic nuclei, but the size of a city, bound by gravity and the strong nuclear force. In some big rip models, the phantom force becomes so strong it exceeds that nuclear binding force. The neutron star would effectively explode, not with fire but with a silent release. Its constituent neutrons, held in that insane density for eons, would be torn apart into a spray of quarks and other fundamental particles. This leads to the most extreme question. What happens to a black hole, a place where gravity is so strong not even light can escape? Its boundary is the event horizon, the point of no return. Some theoretical work by physicists like Sean Carroll suggests that in a big rip scenario, the cosmological horizon shrinks. That's the point beyond which expansion carries light away forever. It shrinks faster than the universe expands, and it eventually gets smaller than the black hole's event horizon. If that happens, the black hole is effectively uncovered. Exposed to the universe, the phantom energy flooding in could disrupt the singularity itself. The black hole would evaporate, not slowly like Hawking radiation predicts, but in a final, instantaneous release, a release of all its stored energy and information. Theoretical physicist Katie Mack has noted the profound strangeness of this idea. It means that in this scenario, nothing provides a final sanctuary. No structure, no object, no law of physics as we know it. The rip claims everything born from stellar death. The white dwarfs, the neutron stars, the black holes, all the possible end states for stars, they're just waypoints on the road to dissolution. This shows the totality of the process. It's hierarchical, working from the largest scales down, but its final goal is the complete dismantling of bound structures, all the way down to the fundamental particles. So after erasing the stars, the last beacons, the phantom force turns its attention to the scale of life itself. To the world we know, the ground isn't solid, it's atoms held together by forces, and those forces have a limit. In the final hours, phantom energy's pull becomes immense. It starts to work on a human scale. The idea of a surface begins to fail. You wouldn't float away, not yet. You'd be standing on a world coming apart. It starts as a vibration, a deep hum felt in the bones. The planet is under stress, pulled from all directions by space itself stretching. That stress moves through the crust. The vibration becomes a shudder, then a constant, violent shaking. This isn't an earthquake. It's the whole planet ringing, like a bell struck by a cosmic hammer. Mountains go first. Their weight, held by rock, is challenged by a force pulling outward. The bedrock stretches. Granite reaches its limit and fractures. A mountain doesn't fall over. It splits silently from peak to base. The phantom force overcomes the bonds between its minerals. It crumbles from the inside. into boulders, then gravel, then dust, all pulled upward into the darkening sky. Think of a steel cable holding a bridge. It has tremendous strength. It resists being pulled apart, but with enough force, it snaps. Phantom energy applies that force to everything. It's a universal tension, increasing until it exceeds the tensile strength of every material. Rock, concrete, steel, they each have a breaking point, and here they all reach it nearly at once. For a last observer, it would be surreal. The ground wouldn't collapse down. It would disintegrate upward and outward. A building wouldn't fall. Its foundations would be pulled away. Then the structure itself would stretch. The bonds between bricks and girders would fail. It would silently unravel into its pieces, each drifting away. The air would thin, pulled into the void, leaving silence, broken by the deep rumble of the planet coming apart. There's no place to run, no shelter. The environment itself is the destroyer. This stage makes it tangible. A cosmological equation becomes the fate of stone and steel. The rip isn't just a distant galactic event. It's a personal unraveling, reducing the world to its physical components. And after that, after mountains are dust and cities are scattered atoms, the phantom force has one frontier left. It has to confront the final bonds, the ones holding atoms together. The dissolution is about to go subatomic. The strongest bonds aren't held by gravity. They're the ones that build everything from nothing. The electromagnetic force, that's what keeps an electron tied to its nucleus. It's what binds atoms into molecules. It's why you can touch something or breathe or even hold together as a physical form. Chemistry is just that force in action, and in the final minutes, phantom energy finishes it. To see how, you have to think about scale. An atom is almost all empty space, a tiny nucleus with electrons orbiting far out. What holds it together is the attraction between the positive protons and the negative electrons. That pull travels at the speed of light. It crosses that tiny gap almost instantly. But space itself is stretching now, and if the expansion, driven by phantom energy, gets so fast that the space between the nucleus and its electron grows faster than light can cross it, then the bond breaks. The signal can't keep up. The photon, the force carrier, falls behind. The electron is cut off, adrift in space that's growing too fast for any message to reach it. You can calculate this, compare the binding energies. The energy to rip an electron from a hydrogen atom is a tiny, known number. The energy density of phantom dark energy, as it approaches the rip, becomes colossal. It floods the universe with a repulsive pressure that overwhelms those atomic bonds. It's like trying to hold two magnets together in a hurricane. The storm wins. The dissolution happens in sequence. First, the weaker bonds go, the van der Waals forces, the hydrogen bonds that give large molecules their shape. Proteins, DNA, the architecture of life, they unravel into simpler chains. Then the covalent bonds, the strong links that hold atoms together in molecules. Water, H2O, splits into separate hydrogen and oxygen atoms. The air, the rocks, your body, every compound breaks apart into a cloud of its basic elements. Chemistry stops, no more reactions, no more structure. Next, phantom energy attacks the atoms themselves. The electromagnetic grip holding electrons in their shells is overcome. Each electron is stripped from its nucleus. What was a cloud of neutral atoms becomes a plasma, a chaotic soup of naked atomic nuclei and free electrons, all flying apart. The last trace of matter, as we know it, is gone. You're not a collection of molecules anymore. You're a diffuse cloud of subatomic particles, each carried off by the stretching spacetime. This moment is more than a physical change. It's the end of information. The patterns in atomic arrangements, the history in a rock, the memory in a brain, all of it is scrambled into noise. The universe loses its structure and its ability to record anything at all. It's the erasure of 13.5 billion years of complexity. all that's left is the final, most fundamental level. Where even atomic nuclei aren't safe, the atomic nucleus is the final fortress, a place of unimaginable density, protons and neutrons packed together by the strongest force we know. The strong nuclear force, it's what holds the heart of matter together, over 100 times stronger than the force that binds atoms. It's the glue that resists the repulsion between protons. Keeps the nucleus stable. For it to fail, the universe would need a pressure beyond anything we've conceived. And in the last instance of a big rip, phantom energy might do exactly that. You have to think about binding energy, the energy holding a nucleus together. When you split a heavy nucleus like uranium, you release some of that energy. It's immense, but to completely tear a nucleus apart, to separate every proton and neutron, requires far more. The total binding energy. For a single proton or neutron to be pulled free, phantom energy's repulsive pressure would need to exceed that titanic value. Particle physicists describe this in terms of quark confinement. Protons and neutrons themselves are made of quarks, held by gluons. The strong force is so powerful that quarks are never found alone. They're perpetually confined. Trying to pull one free is like stretching a rubber band. The energy you put in creates new particles before you can isolate one. The bond doesn't break, it transmutes. The Big Rip proposes a force so absolute it could break confinement itself. As phantom energy density races toward infinity, its repulsive pressure could theoretically surpass the energy density of the strong force field. It wouldn't be like pulling quarks apart. It would be like flooding the universe with a repulsive energy so intense the strong force's binding field is simply overwritten. Swamped, the rubber band snaps without creating new pairs. This is the most speculative frontier. We're applying equations from cosmology to the quantum realm, where our theories of gravity and particle physics clash. No experiment can test conditions of such extreme energy density. It exists at the limit of our models, a place where space-time itself may cease to have meaning. The event is less a physical process we can visualize and more a mathematical endpoint, a point where all structure, all interaction ceases. If it were to happen, the sequence would be swift. First, atomic nuclei would be shredded. The strong force's grip would vanish. Protons and neutrons scattered, but it wouldn't stop there. Almost immediately, the phantom force would turn on those scattered nucleons. A free neutron decays in minutes normally, but here there is no time. The energy density would be so great it could overcome the forces binding the quarks within each proton and neutron. They would disintegrate, not into smaller particles we know, but into a spray of their most fundamental constituents, quarks and gluons. A quark-gluon plasma, instantly and infinitely diluted by expansion. This moment is the ultimate victory of expansion over cohesion. Every known force of nature, gravity, electromagnetism, the strong and weak nuclear forces, each would be overcome, in reverse order of their strength. The universe reduced to a thin, cold mist of the most basic particles, each one isolated by an infinite stretch of space that grows faster than light can bridge. There is no smaller structure to dismantle. This is the final silence. The Big Rip's completion isn't an explosion into something new. It's the end of physics as a story of interaction. It leaves behind a cosmos where nothing can ever happen again. That timeline seems impossibly far away, but it's right there in the math. The question is when. To get at that, you look at one number. Scientists call it the equation of state parameter, W. It's a measure of dark energy's character, its pressure compared to its density. For the cosmological constant, W is exactly -1. That's the baseline, the gentle hum. But for phantom energy, W has to be less than -1. More negative, and the more negative it gets, the faster the clock runs toward the final rip. You can put this on a cosmic calendar. Our universe is about 13.8 billion years old right now. If phantom energy is real, and its W is exactly -1.1, which some models think is plausible, then the Big Rip happens in about 100 billion years from now. That's a future so vast it's almost meaningless, but you can frame it. Our sun will die in 5 billion years. It'll swell into a red giant and engulf the inner planets. The era of star formation, when new suns light up, that'll sputter out in about 100 trillion years. So in this scenario, the rip comes long before the last stars fade, but long after our own star is gone. But if the phantom energy is stronger, more aggressive, the timeline shrinks. If W is -1.5, the rip could happen in as little as 20 to 30 billion years. That's still profoundly distant, but suddenly it feels closer on the scale of cosmic events. It would happen while many of the universe's long-lived red dwarf stars are still shining. Their faint glow would be cut off not by old age but by dissolution. That's the eerie plausibility of it. It's not a certainty, it's a shadow on the far horizon. Current data from missions like the Planck satellite, which mapped the afterglow of the Big Bang, and from supernova surveys, they don't confirm phantom energy. They tell us W is very close to -1, but the measurements have a margin of error. That uncertainty is the space where the phantom scenario lives. The data allows for it, it doesn't rule it out, so the simplest model is a constant dark energy, leading to a cold, lonely future, but the door to a more violent end is still slightly ajar. This framing changes the threat. It's not an imminent danger. It's a potential destiny written into the fabric of the cosmos, waiting to unfold over timescales that dwarf human history. It makes the universe feel like a story with an ending we can't yet read, but whose final chapter we're starting to outline, and it raises a question that shifts things from pure physics to something more philosophical. If this is a possible end, what does it mean for everything that came before? The search for phantom energy is looking for a number, a single digit hidden in the light coming from across the cosmos. That number is W, the equation of state. Is it exactly -1, a constant, or is it something more negative, the sign of a phantom? To know, we have to measure how the universe has expanded with a precision we've never had before. This isn't just speculation now, it's a data problem, and some of the most ambitious astronomy projects ever are trying to solve it. Take the Dark Energy Survey. For 6 years, a powerful camera on a telescope in Chile scanned 1/8 of the night sky. It wasn't just taking pictures, it was collecting light from hundreds of millions of galaxies, some so far away their light has been traveling for over half the age of the universe. The goal was to use 3 different techniques all at the same time to find the truth about dark energy. The first technique uses cosmic mile markers, type Ia supernova. These are the same exploding stars that showed us the acceleration back in the 90s. They have a known brightness, so astronomers can measure how dim they look to get their distance. And by measuring how much their light is stretched, the redshift, they know how much the universe has expanded since the explosion. By finding thousands of these supernovae across huge distances, the Dark Energy Survey builds a map of how the expansion rate has changed over billions of years. Any shift from the expected curve tells you the value of W. The second method uses a fossilized echo from the early universe, baryon acoustic oscillations. In the first few 100,000 years after the Big Bang, the cosmos was a hot, dense soup of particles and light. Pressure waves like sound waves moved through this plasma. When the universe cooled enough for atoms to form, the light broke free and those waves froze in place. They left a subtle imprint, a preferred scale in how galaxies are spaced. That scale is a standard ruler etched into the cosmos. By measuring the apparent size of this ruler at different times, scientists can measure how space has stretched, giving another independent check on the expansion history and W. The third technique is weak gravitational lensing, which maps the invisible. Dark matter, which makes up most of the matter, warps space-time. It acts like a lens, bending the light from galaxies behind it. By studying the subtle distortions in the shapes of millions of distant galaxies, astronomers can make a three-dimensional map of where the dark matter is. This map shows how the cosmic web of matter has grown over time, and because the growth of structure is in a tug of war with dark energy's repulsive push, this map gives a crucial third constraint on its strength and nature. The power of projects like the Dark Energy Survey is combining these probes. It's like checking your location with a map, a compass, and the stars. If all three agree, you can be much more confident you're on the right path. The initial results have been profound, but they point to a universe consistent with a simple cosmological constant. The data so far likes W equals -1. But the uncertainty, the margin of error, still has room for the phantom. This is where the next generation of observatories comes in, on a scale that redefines the search. The Vera C. Rubin Observatory, being built in Chile, will begin the legacy survey of space and time in a few years. Its enormous mirror and giant camera will scan the entire southern sky every few nights for a decade. It won't just observe millions of galaxies, it will catalog billions, it will discover millions of supernovae. This tidal wave of data will shrink the error bars on W to a sliver, potentially ruling out the phantom for good, or, against the odds, finding its first real hint. Meanwhile, in space, the European Space Agency's Euclid telescope is already on its mission. From a point beyond the Moon's orbit, free from the blur of Earth's atmosphere, Euclid is creating the most precise map of the large-scale structure of the universe ever made. Its focus is on measuring the shapes of over 1 billion galaxies to chart dark matter and pin down the baryon acoustic oscillations in detail. They are measuring the geometry and growth of the cosmos to an accuracy of 1%, turning the universe itself into a laboratory for physics. This turns the Big Rip from a thought experiment into a testable scientific hypothesis. The answer isn't written in philosophy. It's encoded in the faint light of ancient supernova, in the statistical clustering of distant galaxies, in the warped shapes of primordial light. We are building the machines to read that code. Within the next decade or two, the data from these monumental surveys could finally tell us if the phantom is real, or if the cosmos is headed for a quieter, if still lonely, end. The search makes you ask a deeper question about our place in a cosmos whose fate we can now seriously try to read. But the Big Rip isn't the only possibility. That whole story hinges on one number we haven't pinned down. If dark energy is just Einstein's cosmological constant, if that value W is exactly -1, then the future is different. It's not a violent end, it's a slow, cold fade, what they call the heat death or the big freeze. Here, the expansion keeps accelerating, but it never becomes infinite in a finite time. It's just an endless climb, asymptotic. The first thing that happens is isolation. Galaxies outside our local group are already racing away, their light redshifting. In about 100 billion years, every galaxy beyond our local family will have crossed the cosmological horizon. They'll vanish, their light stretched to wavelengths we can't detect. For any observer in the merged Milky Way and Andromeda, the night sky will be nearly empty, just a few local stars in an ocean of black, and time stretches on. The last stars, the red dwarfs, they finally burn out. After trillions of years, the last nuclear fires go dark. The galaxy is then just cooling remnants. White dwarfs glowing with leftover heat for eons, neutron stars, black holes. The universe becomes a graveyard of engines that have run down, and then, over timescales so vast they're hard to grasp, even these remnants fade. White dwarfs cool to black, becoming cold spheres of crystallized carbon and oxygen. Neutron stars slowly cool through faint radiation, and black holes, according to Hawking's theory, they're not perfectly black. They emit a tiny bit of radiation, losing mass incredibly slowly. For a stellar black hole, this Hawking process would take far longer than the current age of the universe to matter. But given enough time, on the order of 10 to the 100 years, even the biggest supermassive black holes evaporate. They release their mass as a faint whisper of particles. The end state is maximum entropy, thermodynamic equilibrium. The universe becomes a uniform, thin, cold sea of fundamental particles and radiation. Photons, neutrinos, electrons, positrons, all so far apart they almost never interact. The temperature approaches absolute zero, no more energy gradients, no more work can be done, no more structure. It's a static, eternal silence, the ultimate heat death. So you have these two futures. In one, the big freeze, the universe dies of exposure. It grows cold and dark over near infinite time, everything eroding through slow quantum processes. It's an end of stillness. In the other, the big rip, the universe is torn apart in a final, finite moment. Everything is actively dismantled by a force that overwhelms the very laws holding it together. It's an end of violence which is more profound, which is more unsettling. The slow fade into a timeless, featureless equilibrium where all history is lost to cold dispersion. Or the catastrophic rupture where everything is annihilated in a definitive, almost surgical act. One is a drawn-out sigh, the other a sudden snap. This stark difference is why cosmologists are so focused on measuring that one number, W. It's not abstract, it's the search for the final chapter, the difference between a constant hum and a phantom scream. It determines whether the cosmos expires in its bed or is taken apart in its prime. The data we gather now from telescopes looking to the edge of time is reading that last page, and it asks us to consider what kind of ending feels true to the universe we see around us. Phantom energy creates a serious problem for physics. For a big rip to happen, the dark energy parameter W has to be less than -1. But that mathematical condition violates a core principle in general relativity. It's called the dominant energy condition. Energy shouldn't travel faster than light. Observers should always measure positive energy density. Phantom energy breaks that rule. Its negative pressure is so extreme it could make spacetime unstable. That instability might allow for closed time-like curves, where cause and effect could break down. So phantom energy might not be compatible with a stable universe. Many theorists see this as a major problem for the Big Rip idea. Then you move to quantum field theory. The world of particles and forces, a phantom field there would have negative kinetic energy. Kinetic energy is the energy of motion. It's always positive. A rolling ball has it, an orbiting electron has it. Negative kinetic energy is deeply problematic. It could make the vacuum of space decay uncontrollably. It could create particles from nothing, breaking conservation laws. Robert Caldwell helped propose the Big Rip. He points out the math in cosmology is clear. But building a consistent quantum field theory that produces phantom energy without catastrophic instability is an unsolved problem. Writing an equation is one thing. Showing it fits into a stable, complete theory is another. This leads to the biggest unknown, quantum gravity. The final moments of a Big Rip involve energies and expansion, rates so high that general relativity breaks down. Space and time would be governed by wild quantum fluctuations. We don't have a theory like string theory or loop quantum gravity that can say what happens then. It's possible quantum gravity acts as a regulator, the way quantum mechanics stops electrons from falling into a nucleus. Quantum gravity might stop the expansion rate from reaching infinity. It could smooth out the singularity, turn the violent rip into a transition to something new, a state beyond our current physics. so the Big Rip might not be a firm prediction. It might be a signpost. It shows where our classical theories fail. It highlights the need to unite gravity and quantum mechanics. Where does that leave the hypothesis? It's still a possibility. It sits within the margin of error of our observations, but it faces deep theoretical objections, questions about its very foundation. This tension isn't a weakness, it's how science works. The Big Rip forces physicists to confront the limits of their models, to stress-test general relativity and quantum field theory. It drives curiosity, pushing the next generation of telescopes and theorists to look for answers. The ultimate fate of the universe might not be a rip or a freeze. It might be something our mathematics hasn't yet dreamed of. The most precise prediction ever made in science is also the most wrong. It's about the energy of empty space. Quantum field theory says the vacuum isn't empty. It's a bubbling foam. Virtual particle pairs pop into existence. They borrow energy for an instant, then annihilate. Every cubic centimeter of nothing should be packed with this vacuum energy. You add up all the contributions from every known quantum field. You get a theoretical number for the energy density. It's an immense positive value that should act as a cosmological constant, a repulsive force driving the universe apart at an incredible rate, but we've measured the actual cosmological constant. The dark energy driving the acceleration, it's a tiny positive number. The discrepancy isn't a small error, it's a factor of 10 to the 120th power. A 1 with 120 zeros after it. It's the worst mismatch between theory and observation in all of physics. That's the cosmological constant problem. It means our best theory of the very small quantum mechanics and our best theory of the very large general relativity are giving answers about the same thing. And they disagree by an amount so vast it defies language. It suggests we're missing something fundamental. Maybe the quantum contributions are cancelled out by some unknown symmetry. Maybe our understanding of gravity breaks down on cosmic scales, or maybe the vacuum energy isn't constant. Maybe it's dynamic, and we're just seeing its current quiet value. This problem casts a long shadow over any talk of dark energy's future. If we can't explain why its value is so small today, how can we be confident it will remain constant forever? Or that it will evolve into a phantom? The Big Rip scenario depends on a very specific, evolving behavior. But our foundational theories are in profound conflict about the very nature of the energy we're trying to predict. That makes any long-term forecast deeply uncertain. Whether it's a gentle freeze or a violent rip, the cosmological constant problem is a glaring signpost. Our map of reality is incomplete. Solving it might not just tweak our models. It could reveal that dark energy is something entirely different than we imagine. It could show the fate of the cosmos isn't a simple choice between two endings. It could be a story with possibilities we haven't yet begun to conceive. The final chapter isn't just unknown. The book itself might be written in a language we're still learning to read. Our cosmic story could be just one chapter. If the Big Rip happens, it might be local, confined to our bubble. An infinite multiverse could carry on untouched. This comes from eternal inflation. The very beginning, the Big Bang, wasn't a single explosion. It was the start of an endless expansion of a primordial field. That's inflation, and it never completely stops everywhere. In most regions, it slows. It ends in a Big Bang, creating a universe like ours. But in other regions, it continues forever, spawning new inflationary regions endlessly. Our entire observable universe, all its galaxies and dark energy, is just one bubble that stopped inflating, a stable pocket in an eternally inflating sea. The key is the vacuum state, the energy of empty space. In eternal inflation, different bubbles can have different vacuum energies. They nucleate, like bubbles forming in a boiling pot. Our bubble has a specific vacuum energy that manifests as our particular dark energy density. A big rip would occur if that vacuum energy has those phantom properties. But in the grand multiverse, other bubbles could have entirely different fates. Some might collapse in a big crunch, others might expand forever with a gentle constant. Their physics could be different, their fundamental constants might not match our own, even the number of dimensions. This leads to a thought. A big rip might not be the end of all existence. It might be the end of our particular configuration. While our space-time tears itself apart, an infinity of other universes would continue, unreachable and forever separate. The multiverse is a kind of cosmic insurance. No single catastrophe can erase reality itself. There's another escape route, more theoretical, from within our own bubble. Some versions of string theory suggest our vacuum state might not be perfectly stable. It could be a false vacuum, a local low point in a landscape of possible energies. Given enough time, and the timelines for a rip are long, quantum tunneling could occur. Our universe could spontaneously transition to a different vacuum state. One with a lower dark energy density or even zero. This event would be catastrophic. A new bubble of true vacuum would form somewhere. It would expand at nearly the speed of light. Its wall would be a wave of new physics, rewriting the laws of nature as it passed. Any structure it encountered would be obliterated. But on the other side of that wall, the conditions for a big rip would no longer exist. The phantom energy would be gone, replaced by a new, stable vacuum. The end would be averted, but at the cost of transforming everything into something unrecognizable. These aren't predictions, they're glimpses at the outer limits of thought. They show how our understanding of fate is tangled with questions about reality's foundation. Is our universe all there is, or is it one island in an endless archipelago? Is our physics permanent, or is it a temporary arrangement waiting to decay? The Big Rip forces these questions open. It makes the far future a laboratory for speculation, and it reminds us the story of the cosmos is still being written. In theories and equations by those who look beyond the horizon, a universe that ends makes you wonder what any of it meant. If the final state is just a cold, thin mist of particles, spread so far apart they never interact again, then what happens to everything that came before? All those billions of years, stars forming, planets, life, consciousness, is it erased, or does the journey matter on its own, no matter where it ends? That's where astrophysics meets philosophy. It asks about the value of a temporary existence. Carl Sagan said we're a way for the cosmos to know itself. In a big rip, that self-knowledge has a final deadline. The universe learns about itself, builds complexity, and then gets taken apart. You have to ask if that's a tragedy or just the natural arc of a story. Some traditions find a deep beauty in things that don't last. A cherry blossom is valued because it's fleeting. Could you say the same for galaxies, for civilizations? Their brief flash against the dark might be what gives them weight, and that's a different vision from other ideas of cosmic fate. Many models imagine a cyclical universe. A big crunch leading to a new bang, expansions and contractions forever. In those, nothing is ever truly lost. Energy gets recycled. Time is a circle. But the Big Rip proposes time as a line with a full stop. That changes the narrative completely. A cyclical cosmos suggests endless opportunity, a second chance or a millionth chance for everything to happen again. A linear cosmos with a rip suggests a single performance, one that can't be repeated. Which one feels more true to how we experience time? We remember the past. We anticipate the future. We move in one direction. The rip takes that intuition to its ultimate conclusion. Brian Greene has wondered if an end gives the universe a shape. A story needs a beginning, a middle, and an end to have coherence. Without an end, the cosmic tale is just an endless middle that can feel strangely unsatisfying. No narrative arc, a definitive end, however violent, provides a framework. It makes the universe's history a closed book, something you could, in principle, understand from start to finish. But that finality can also feel nihilistic. If all structure, all memory, all information gets scrambled into noise in the end, then does any achievement matter? Any discovery, any act of love or courage, does it have lasting significance, or is significance something that exists only within the story, not after it? That tension is at the heart of this. It asks if meaning comes from permanence or from the quality of the moment itself. This discussion isn't about providing answers. It's about sitting with the questions. The possibility of a big rip stretches how we make meaning. It forces a confrontation with scale. Our lives are decades. Our civilizations are millennia. The cosmos operates on billions of years, trillions. To find that even these vast epochs are not eternal, that they too might have an end, is a humbling thought. An awe-inspiring one. It connects the astrophysical to the deeply human. It makes our brief candle flame of awareness not less remarkable, but perhaps more so. A flicker of light and understanding in a cosmos that may one day forget light entirely. That pause for reflection is necessary, because after considering implications that vast, you have to come back to a more immediate question. A practical one. If this is a possible future, should we ever try to do anything about it? Could we? The idea of the end of everything, it's too big to just stay in the math. It always moves into our stories, our movies. Science fiction has always been a place to test these fears, and a universe tearing itself apart, that's a different kind of ending. It's not a black hole which eats things. It's not a supernova which is a local destruction. The Big Rip is a systematic unmaking, an apocalypse without a villain. The catastrophe is just written into the rules, the laws of physics that makes it a powerful story. The conflict shifts. It's not about external monsters. It's an internal race, a race against a clock that doesn't care. You can see it in Doctor Who. That show is built on time and consequence. There's a story where the Doctor finds a reality. The universe is aging too fast. The fundamental constants are decaying. Stars are going out, not because they ran out of fuel, but because reality itself is failing. The story isn't about fighting a fleet. It's a desperate search for a cause, a flaw in the universe's code. The horror is in the silence, the fading light. The characters aren't trying to save the galaxy in a battle. They're trying to save the concept of physics in a library that captures the rip's essence. The enemy isn't something you can reason with or shoot. It's the stage collapsing under the actors. Star Trek has gone there too. That's usually an optimistic show, but episodes have explored spatial rifts. Dimensional tears, subspace fractures that threaten to unravel local spacetime. It's not the full cosmological rip, but the storylines use the same language. The same feeling. A starship crew doesn't face a warlord, they face a creeping anomaly. Their struggle is about measurement, containment, and finally, acceptance. The drama comes from watching advanced technology, advanced intellect grapple with a force that operates on a scale beyond engineering. It turns engineers into philosophers. Asking what you do when the rules you depend on start to dissolve. The literary world goes deeper. Alastair Reynolds, he's an astrophysicist who writes. He crafts hard science fiction where cosmic scales are characters. In his novel House of Suns, civilizations exist over millions of years. The threat isn't just a dying star. It's the potential for galactic-scale disasters, disasters that erase history. It's not a direct big rip, but the atmosphere is saturated with deep time. The fragility of memory against the cosmos. It explores what legacy means when your monuments might be atomized by a physics you can't control. The characters are clones who live for eons. They're obsessed with recording everything, preserving memory against an entropic tide. That's a cultural response to the fear the rip embodies. the complete erasure of information. If everything you are, everything you did can be scrambled into noise, what's the point of doing anything? The novel suggests the point is the doing itself. The act of witness, even if the witness is ultimately lost. These stories share common things that make a RIP scenario different. Visually, it's not shown with fire. It's shown with distortion. Stars don't explode, they smear or wink out silently. Space itself warps like a film projection melting. The sound design shifts. From roars to deep, subsonic groans or to eerie silence. Narratively, the focus is on desperation, not heroism. Plans are futile. The climax is often a bittersweet act of preservation. Saving a single data core, launching one last message into the void, or simply bearing witness until the final moment. The enemy is time, and time always wins. This cultural absorption, it serves a purpose. It acts as a bridge. The raw data from a telescope is abstract. A story about a crew watching their ship come apart at the atomic level that makes the physics personal. It translates the equation into a heartbeat. When an artist grapples with phantom energy, they're doing public philosophy. They're asking the questions we all might ask. But framed through character and conflict, they explore legacy, the value of temporary beauty, the human urge to find meaning even in the face of absolute finality. By weaving these ideas into narrative, science communication finds an ally. A viewer might not remember the exact value of a parameter, the equation of state. But they might remember the haunting image of a silent, stretching sky from a film. That image becomes an anchor. Later, when they hear a scientist discuss the fate of the universe, they have a reference point. A feeling, the art seeds the concept, the science gives it form. This creative dialogue, it's how humanity has always processed existential threats. We tell stories about them. From myths of great floods to novels about cosmic rips, we use narrative to walk to the edge of the abyss, look down, and then step back, having made the unknown a little more familiar. Could a civilization fight back? Could intelligence, given enough time, survive the end of everything? It's a thought experiment, a society trillions of years in the future. They would have mastered energy on a scale we can't comprehend, the Kardashev scale. A Type 2 civilization uses the energy of its star, a Type 3 the energy of a galaxy. A Type 4 might manipulate the energy of the universe itself. They would be like gods. They could build megastructures, move stars, engineer black holes for power. They might create self-sustaining arcs, sealed against the cold, carrying the last embers of consciousness. Their ultimate project might be escape, not to another star, but to another reality. The theoretical physics of our time suggests possibilities. If they understood string theory, they might tunnel into a different vacuum state, a stable pocket of space-time with kinder physics. They could try to create a baby universe in a lab, a bubble of new reality, and slip inside before the rip consumed the old one. Or they might try to manipulate the fabric of their cosmos, to stabilize the phantom field, to turn the tide through cosmological engineering. Futurists like Michio Kaku have explored this. The drive to survive, to preserve knowledge, would be a powerful motivator across eons, but then you reach the wall of fundamental physics. The Big Rip, if it's driven by true phantom energy, isn't just a powerful force. It rewrites the rulebook. It doesn't just pull things apart. It changes what it means to be bound together. First, it overcomes gravity, then electromagnetism, finally, the strong nuclear force. No structure is safe because the force operates at the level of space-time itself. You can't build a wall against a tide that rises within the very bricks of the wall. An engineer can design a ship to withstand any storm by making it stronger. But what if the storm's fury also weakened the molecular bonds in the hull? The stronger you build it, the more violently it comes apart. The rip doesn't attack from outside. It compromises the internal cohesion of everything. A civilization could gather all its energy, all its matter, into one final, dense fortress. But as the phantom force grew, that fortress would face the same tidal stresses as a planet. Its atomic bonds would fail, its information would be scrambled. There is no hiding place because the arena of existence itself is being dissolved. This leads to an insight. There may be cosmic limits to what any agency can achieve, no matter how intelligent. Some forces are not challenges to be overcome, but conditions to be accepted. Phantom energy suggests the cosmos holds a final authority, a set of boundary conditions that not even supreme intelligence can negotiate. The story ends not with a battle, but with a transition dictated by the deepest laws. That doesn't render the journey meaningless. Their struggle, their art, their wisdom across trillions of years existed. It was real. Its value wasn't contingent on lasting forever, but on being expressed at all. In facing the rip, such a civilization would confront the ultimate question of legacy, finding that perhaps the only thing you can preserve against the void is the dignity of how you meet it. Dark matter is the quiet one in all of this. It built the stage, but it doesn't speak in the final act. Its role is simple. It's the gravitational glue. The invisible scaffold that let galaxies form in the first place. Its particles, whatever they are, don't give off light. They hardly interact with each other or with normal matter. They just feel gravity, and with dark energy expanding everything, that becomes a real problem. The phantom force treats dark matter the same as anything else. It stretches the space-time it's in. Think of a galaxy like ours. It's not just stars. It's sitting inside a huge, spherical halo of dark matter. That halo is the real anchor. The stars orbit inside its grip, but when the rip starts, that halo is just as exposed. The phantom energy doesn't fight it. It just expands the space the halo occupies. The dark matter particles, held only by their gravity, feel those bonds stretch. A halo that's hundreds of thousands of light years across begins to swell. The outer parts get pulled away first, the particles drift, their gravitational link gets weaker, and eventually the whole halo dissipates. It doesn't collapse. It just dilutes, like ink in an ocean that's itself getting bigger every second. The dark matter becomes a thin mist, its particles so far apart they might as well be alone. This passive end shows the split between the two dark components. Dark energy is the active one. It's the driver, the source of the repulsive pressure working against gravity. Dark matter is reactive. It's a passenger. It shaped the past, but it can't do anything about this future. It just gets carried along, its influence fading as the space between particles becomes a gulf. That separation is important. It means in the final moments, even the most dominant form of matter, over 85% of all matter, is powerless. The structure it spent billions of years building is taken apart by a force it can't touch or feel or resist. The silent witness watches everything it helped build come apart before it too is scattered into the growing dark. This passive dissolution finishes the hierarchy. The rip claims everything from the biggest galaxy clusters to the most elusive particles. No structure is left, visible or invisible. The end could still make a sound, a vibration in space-time. This phantom force tearing galaxy clusters apart, shredding neutron stars, it would generate gravitational waves. They're not sound, they're ripples in the geometry of things. Einstein predicted them. We've seen them from black holes colliding, but this process would be catastrophic. A galaxy cluster gets pulled apart. Its immense mass accelerates violently. That acceleration, that sudden shift in where gravity comes from, sends tremors through space-time. These waves would be incredibly long, wavelengths spanning millions of light years. Frequencies so low a single oscillation takes years or centuries. They'd be a chorus of deep groans, each one marking a cosmic giant dissolving. The most powerful signals might come from the last compact objects, a neutron star. When phantom energy overcomes the nuclear force binding it together, that city-sized ball of density gets stretched, disrupted, a final, violent event. The release of gravitational binding energy would be immense. It would ring space-time like a bell, a final, deafening bell, but who's left to hear it? By this stage, any civilization is fighting for its own structural integrity, building a detector sensitive enough while the detector's own matter is being pulled apart. It's a paradox. The waves themselves pass through space-time, but space-time is stretching at a catastrophic rate. It could distort the signals, redshift them into oblivion. Some models push further, the moment of the rip singularity where the expansion rate becomes infinite. It could act like a cosmic event horizon. The violent quantum fluctuations at that boundary might generate a burst. Primordial gravitational waves imprinted on the fabric of reality, a fossilized tremor from the last moment you could call it a universe. They would, in theory, persist, propagating through whatever comes next, but they'd be utterly undetectable from within. No apparatus left to measure them, no observers to record the data. This signal is a message with no recipient, a final note for an empty hall. The concept is profound, though. It links this speculative end to modern astronomy. Today, observatories like LIGO listen for the chirps of colliding neutron stars. In the far future, the last gravitational waves might be the dying screams of those same stars. Taken apart not by each other but by the universe itself, it suggests an ending of total dissolution might not be completely silent. It might resonate, leaving a faint, rippling signature on the boundary of existence, a final testament written in the warping of space-time for an audience that may never be. There's another possible end for the cosmos, a sudden kind of unraveling written into the quantum fields that fill all of space. It's called vacuum decay. The idea is that our universe sits on a foundation that isn't perfectly stable. It's metastable, a false vacuum. Imagine a valley high up on a mountainside. It looks comfortable, stable. You could stay there for eons, but far below there's a deeper valley, a true vacuum with lower energy. Our universe is in that high valley. And quantum theory says there's always a tiny chance, a non-zero chance, that a bubble of that lower energy state could just form, spontaneously. It would be a quantum tunneling event. A random fluctuation so unlikely it's almost impossible. But given infinite time, maybe it's inevitable. This bubble wouldn't be made of matter. It would be a region of space where the fundamental laws of physics are different, where the Higgs field, which gives particles mass, has a different value, where the constants of nature, the strength of gravity, the charge of an electron are rewritten. And this bubble would expand at the speed of light. Its wall, a boundary of unimaginable energy, would be a wave of new physics sweeping across everything. Anything it touched would cease to exist in any form we know. The atoms in your body would lose their cohesion. Their properties would change instantly. All structure from planets to stars to galaxies would be erased, not by being pulled apart, but by having the rulebook of reality swapped out. It's an end by redefinition. Now compare that to the Big Rip. Both are swift, both are total, both erase everything we know, but their engines are different. The Big Rip is a classical gravitational phenomenon. It's driven by the large-scale dynamics of space-time, by expansion overwhelming the forces that bind things. It works from the outside in. It dismantles structures in an order. Vacuum decay is a quantum phenomenon, a phase change like water spontaneously freezing. It starts at a single, random point and expands, changing the fundamental properties of the vacuum itself. It doesn't pull things apart. It transforms what they are made of from the inside out. There's a chilling intersection here. The presence of phantom energy, with its negative pressure, could theoretically influence the vacuum's stability. Some calculations suggest a phantom field could lower the energy barrier between our false vacuum and a true one. It could make the mountain slope between the valleys less steep. That would dramatically increase the probability of a quantum tunnel. So in this interplay, the very force driving a big rip could also trigger a vacuum decay event. Long before the rip's timeline concludes, one apocalypse could preempt the other. This layers the stakes. We're not just measuring one parameter to see if we face a rip or a freeze. We're also probing the quantum landscape to see if our valley is truly secure, or if a deeper one calls from below, and that invitation might be made more urgent by the dark energy stretching the hills around us. It means the ultimate end might not come from the relentless pull of expansion, but from a single, random quantum burp in the fabric of nothingness, a bubble of true reality that consumes its false parent. Without a sound, our existence is balanced on a knife's edge. The numbers that run the universe, the fundamental constants, they seem finely tuned. If gravity were just a bit stronger, stars would burn out too fast. If the strong nuclear force were a bit weaker, atoms wouldn't form, and dark energy is the strangest case. The value we see is incredibly small, but it's not zero. It's just enough to drive the acceleration we observe, but not so much that it tore everything apart before galaxies could even form. If it were slightly larger, a big rip could have happened in the universe's infancy. The fact we're here looking at a structured cosmos might be telling us something about its ultimate fate. That line of thinking is called the Anthropic Principle. In its simplest form, it says the universe we see has to be compatible with observers existing. We can't find ourselves in a universe that doesn't allow for us. So when we measure dark energy and find this peculiar, tiny value, one question comes up: could a universe that ends in a big rip ever produce observers? The answer might be yes, but with a strict deadline. For life to arise, you need stable atoms, planets, stars, and billions of years of cosmic evolution. A big rip scenario, depending on when it happens, could allow for that. If the rip is scheduled for, say, 100 billion years from now, that gives life plenty of time to emerge in the eons before. So our existence doesn't rule out a rip. It just requires that the rip's countdown is long enough to allow for creatures who can think about it. This leads to a dizzying possibility. The multiverse. If our cosmos is just one bubble in an endless froth of universes, each with different physical laws and constants, then most of those universes would be stillborn. Too much dark energy and they rip apart instantly. Too little and they might collapse too soon. Only in a narrow slice of this cosmic landscape, where the parameters are just right, do you get a universe old enough and stable enough for observers to evolve. We find ourselves in that slice not because it's special, but because it's the only kind we could ever find ourselves in. Our very presence is a filter. It selects for universes where the end is not so immediate that it prevents the beginning. So the quiet value of dark energy we measure today might be a clue. It could be the signature of a universe poised on a boundary, one that allows for a long, fruitful period of structure and life, but whose underlying physics still points toward a final dissolution. The rip isn't an anomaly. It could be the inevitable outcome of the same delicate balance that made our existence possible. The forces that allow atoms to hold together for 13 billion years might contain the seeds of their own undoing. This connection ties our origin story directly to our final one. The universe that gave us life may have written its expiration date into the same equations. We're not just passive observers of this fate. We are, in a deep sense, products of the conditions that make that fate possible. Our ability to ask the question is part of the answer. The most violent beginning the universe ever had might tell us something about its most violent end. That first moment, the Big Bang, was actually preceded by something else. A fraction of a second called cosmic inflation, and this wasn't the slow expansion we see now. It was space itself exploding outward exponentially, driven by a different kind of vacuum energy. A field that filled everything with a repulsive force so strong it doubled the size of the universe over and over, in timescales you can't even imagine. Alan Guth proposed this to solve puzzles: why the universe looks so uniform, why it's so flat on the largest scales. The engine was a scalar field, rolling slowly down a hill of potential energy. And as it rolled, it released energy, and that drove the hyper-expansion. The key number is the Hubble parameter, the rate of expansion. During inflation, that parameter was huge. But it was also nearly constant because the energy density of that inflating field was so stable. The universe expanded exponentially fast, but the engine itself was steady. Now you take phantom energy, the thing that could cause a big rip. The mechanics sound similar on the surface. Both are a form of vacuum energy causing runaway expansion. Both have the Hubble parameter at the center, but the outcomes are perfect opposites. Inflation was creative. When it ended, that primordial field decayed. Its energy transformed into the hot soup of particles that became our universe, and the quantum fluctuations in that field, tiny ripples, they got stretched to cosmic size. They became the seeds for all structure. The galaxies we see grew from those microscopic wrinkles. Inflation built the canvas. Phantom energy does the reverse. Its expansion isn't creative, it's destructive. Its Hubble parameter doesn't stay constant. It accelerates toward infinity. Instead of seeding galaxies, it takes them apart. Systematically, the symmetry is haunting. One epoch of extreme expansion writes the first chapter of structure. A future epoch of extreme expansion could write the last. The universe's story could be bookended by two kinds of vacuum energy, one giving birth to everything, the other taking it all away. This parallel raises a question. Can we use the same math to understand both? Inflation is described by models of scalar fields. Phantom energy is often described the same way, but with a crucial twist. A problematic one. A phantom field would have negative kinetic energy. That leads to instabilities, so the equations might look similar, but their physical foundations are profoundly different. Studying inflation gave us insights into how vacuum energy can shape spacetime. Applying those lessons to phantom energy shows us where the models break down. Where a creative force becomes a destructive one, this framing turns the cosmic story into a possible arc, from an explosive, structure-creating beginning to a violent, structure-destroying end. It's not a cycle. The rip doesn't lead to a new bang. It's a one-way journey from one form of exponential expansion to another, with 13.8 billion years of complex, beautiful life in between. Seeing this connection enriches the narrative. It suggests the fate of the cosmos isn't a random accident. It's a possibility woven into the same fabric of physics that allowed it to exist in the first place. The force that made the universe capable of bearing life might also carry the instructions for its final unmaking. General relativity is a theory of gravity. It's passed every test for over a century. It describes the cosmos as a fabric, a dynamic fabric that bends under mass and energy. It dictates the motion of planets. It dictates the expansion of the entire universe. The equations that predict a big rip, the Friedmann equations, they come directly from this theory. They take the ingredients of the cosmos, matter, radiation, dark energy, and they project their future. But what if those equations reach a point where they can no longer be trusted? What if the theory itself breaks down? Every great theory has its limits. For Newtonian gravity, it was the orbit of Mercury. It was the speed of light. For general relativity, the limits appear in realms of extremes, unimaginable extremes. At the center of a black hole where density becomes infinite, the equations produce a singularity. A point where the math fails, where physics becomes meaningless. Similarly, at the very beginning, the Big Bang is described as another singularity. Our theory of the very large cannot handle the conditions of the very small and dense. This is the domain of quantum mechanics, a realm of probability and uncertainty. It has never been peacefully united with Einstein's deterministic geometry of spacetime. The final moments of a big rip present a similar frontier but in reverse, not infinite density but potentially infinite expansion, a rate of expansion racing toward infinity, stretching spacetime itself beyond any recognizable scale. In such a regime, the classical, smooth fabric of general relativity might shatter. It might shatter into a frothing quantum foam. The equations we use to predict the rip assume spacetime remains a continuous stage, but at these extremes, the stage itself might be made of indivisible pieces. Like a digital image breaking into pixels when you zoom in too far. This is where candidate theories of quantum gravity enter the story. They are attempts to write a new rulebook for these ultimate conditions. String theory, for instance, proposes that the fundamental building blocks are not point-like particles, but tiny, vibrating strings. Their different vibrations give rise to all forces and particles. In some versions of string theory, the equations suggest new kinds of repulsive forces, or modifications to gravity at high energies that could prevent a true singularity. The phantom energy driving the rip might encounter a quantum wall, a fundamental limit to how fast space can stretch, turning the violent rupture into a transition. Another approach is loop quantum gravity. It imagines spacetime itself as woven from a network of finite loops. Space is not infinitely divisible. It has a smallest possible scale, a quantum of volume. In this picture, as you trace the expansion of the universe backward toward the Big Bang, you don't hit a singularity. Instead, you reach a point of maximum density where quantum gravity effects create a powerful repulsion. A big bounce, the collapsing universe rebounds into a new phase of expansion. Applied to the far future, could a similar quantum repulsion emerge as expansion reaches its maximum possible rate? Perhaps the universe, instead of ripping, reaches a kind of elastic limit and rebounds. It rebounds into a new cycle, a cosmic heartbeat where contraction follows expansion in an endless rhythm. These ideas are not yet proven. They are maps of territories we have not yet observed, but they serve a purpose. They remind us that the Friedmann equations and the stark future they paint are based on a theory we know is incomplete. The true fate of the cosmos may be governed by laws that blend general relativity and quantum mechanics in ways we have not yet imagined. The Big Rip might be a ghost in our current mathematics. A prediction that vanishes when a more complete theory takes the stage. This is the humbling frontier of cosmology. We have used our best tools to peer billions of years into the future, only to find that at the very edge of our vision, the tools themselves begin to blur. The search for the universe's end is paradoxically a search for a deeper beginning, a more fundamental understanding of reality. It tells us that the final chapter of the cosmos might be written in a language we are still learning to speak. A reminder that the greatest discoveries about our place in the universe may still lie ahead. To model the end of everything, you need a universe in a box. A digital one, the equations for cosmic expansion from general relativity, they're complex, non-linear. There aren't simple pen and paper solutions for a universe with galaxies, dark matter, a phantom energy field. So that's where computational cosmology comes in. It turns the theory into a visual story. Scientists take the best data we have, the cosmic microwave background, how galaxies are distributed, and they feed it into the most powerful supercomputers. They program in the laws of physics. They set the initial conditions from the early universe. Then they press play. The computer calculates the gravitational dance for trillions of dark matter particles. It simulates how they clump, how they form the cosmic web over billions of years. That's the foundation. Projects like the Millennium Simulation did this. They created a virtual universe that matched our own. To study dark energy's future, you introduce a new actor into the code. You change the parameters. You tell the simulation the cosmological constant, W, is not -1. It's something less. You inject the phantom. Then you run the simulation forward. You watch the digital cosmos evolve. The first thing you see is the large-scale structure responding. The filaments of the cosmic web, those highways of galaxies, they begin to stretch. They thin, the connections between superclusters sever. The virtual sky, once full of connected light, starts to empty out. Galaxies become isolated islands. This isn't a movie of the actual rip. It's a visualization of the early and middle stages from the equations. It shows the hierarchical dissolution in action from the outside in. The simulations reveal timelines. For a given phantom energy value, they can estimate when a galaxy cluster like Virgo would become unbound from its neighbors, or when the local group would stop its inward dance and begin to drift apart. These are statistical forecasts built on millions of hours of processor time. But the simulations hit a wall, a fundamental one. They can model the dissolution of gravity-bound structures beautifully, but the final act, the moment phantom energy overwhelms nuclear and atomic forces that exists in a realm beyond their reach. The physics of quantum gravity, of spacetime singularities, isn't something you can just code. The scales become too extreme. Simulating the rip of an atomic nucleus would require modeling quantum fields in an exponentially stretching spacetime. A problem with no computational solution right now. So these cosmic forecasts are like weather models for the universe. They can give a detailed picture of the storm's approach. The rising winds, the dropping pressure, but the precise moment the tornado touches down, the physics at the very center of the vortex that remains in the realm of theory. Yet this digital experimentation is invaluable. It lets scientists ask what-if questions. What if the phantom energy parameter is -1.05 versus -1.2? The difference in the timeline becomes clear. The visual progression of the dissolution becomes clear. It turns a frightening idea into a quantifiable, testable set of predictions. By comparing these simulated futures to our ever-improving maps of the real universe, we can look for subtle signs. Is the clustering of galaxies at the largest scales beginning to show the faint signature of an extra repulsive force? The simulations tell us what to look for. This blend of raw theory, massive computation, and precise observation, that's how modern cosmology operates. It moves us from philosophical speculation about the end of time to a rigorous, if still uncertain, scientific investigation. The universe in the supercomputer is a shadow of our own. A guide to possibilities written not in stone, but in light and logic and the silent hum of processors working through the night. That image of a universe tearing itself apart, it's a strong one. And strong images tend to get twisted. Time is one of the big confusions. The big rip isn't happening now. We can't observe it. It's a possible future, and it depends on a specific kind of dark energy we haven't proven exists. We're not being shredded. Everything we see, our galaxy, distant clusters, they're all still bound. They're stable on our timescale. The rip is a forecast. Its timeline is tens of billions of years out, long after our sun is gone. Thinking it's imminent is like boarding up your windows for a storm 1,000 years from now. Then there's the mix-up with black holes. The rip isn't the universe falling into a giant singularity. A black hole pulls everything inward toward a point. The big rip is the opposite. It's an outward force, a repulsive pressure that pushes everything away from everything else. It's not a pull into a pit. It's a stretch into a void. You wouldn't be spaghettified toward a center. You'd be pulled apart from all directions at once, like dough being stretched thinner and thinner until it's gone. That brings up motion. When we say the universe is expanding, we don't mean galaxies are flying through space like shrapnel. They're mostly stationary within the fabric. It's the fabric itself that's stretching. Think of raisin bread dough. As it rises, every raisin moves away from every other raisin, not because the raisins are traveling, but because the dough between them expands. In the rip, the oven gets hotter. The dough doesn't just rise, it stretches so violently the raisins themselves are torn apart. This expansion is also different from a recollapse. The big crunch, that's where gravity wins. It reverses the expansion, pulls everything back into a hot, dense state, a cosmic contraction. The rip is the ultimate victory of expansion over contraction. They're two opposite endings, one a crushing reunion, the other an infinite separation. Media lumps them together, but the physics couldn't be more different. Then there's force. The rip isn't an active, intelligent force hunting things down. It's a passive condition, a property of space that becomes overwhelming. It doesn't seek out galaxies to destroy. It just creates an environment where no bond can endure. The tragedy isn't a malevolent act. It's the slow, inevitable change of the rules. Understanding these distinctions cleans the lens. It moves the idea from a vague sci-fi catastrophe to a specific physical process, a speculative one. A process whose truth will be decided by the cold, hard light from the edge of time. Why should we care about a future we'll never see? The answer isn't in the stars. It's in what the search asks of us, this drive to map the ultimate fate of everything. It's not a luxury. It's a core expression of human curiosity. The same impulse that paints a sunset, that writes a symphony, that builds a philosophy. It's looking beyond the horizon of our own existence and asking what's out there. When we measure the faint light of a supernova 10 billion light-years away, we're not just collecting data. We're seeking context, our place in a story that goes from a hot, dense beginning to a cold, expansive end. That knowledge has value. It cultivates a cosmic humility. It reminds us that our dramas, our triumphs and hardships, they're set on a stage of almost incomprehensible scale and duration. This perspective doesn't diminish our lives. It frames them. It asks us to consider what matters in the fleeting time we have. This grand quest also gives tangible gifts right now. The technology forged to chase these questions doesn't stay locked in an observatory. To detect the subtle dimming of a distant star, engineers had to invent cameras of breathtaking sensitivity. The charge-coupled devices, the CCDs, that now guide surgeons in minimally invasive procedures. Tracing blood vessels with exquisite precision, the algorithms developed to filter cosmic noise from telescope data. They now help model climate patterns or analyze complex financial markets. The precision spectroscopy used to measure a galaxy's redshift is the same technology that can detect trace pollutants in our atmosphere or identify new materials in a lab. The search for dark energy, for phantom fields and cosmic rips, it pushes the boundaries of optics, computing, material science. It solves problems we didn't know we had, creating tools that improve medicine, safeguard our environment, drive innovation. The journey to understand the end of time quietly builds a better today. And this long view, this contemplation of deep time and cosmic fate, it can reshape how we think about our own legacy. If we accept that our civilization, and maybe even our planet, are temporary waypoints in a vast cosmic journey, it reframes our responsibility. It asks not for despair but for thoughtful stewardship, the drive to preserve knowledge, to build resilient systems, to create beauty and understanding that might outlast us. These aren't acts of vanity. They're affirmations of value within a transient universe. They're our way of etching a message, however faint, into the cosmic record. Exploring the Big Rip isn't an exercise in doom. It's an exercise in meaning-making. It connects the most fundamental forces governing reality to the most human of questions. Why are we here, and what do we do with the time we have? By tracing the possible end of the cosmos, we are, in a very real sense, defining what we believe is worth preserving at its beginning. That's the final justification for this journey. Not because we fear the end, but because understanding it helps us appreciate the extraordinary, fragile middle in which we find ourselves living. The equations are clear. But the reality is still a profound mystery. Our map of the cosmos has these vast blank spaces, and dark energy sits right in the middle of that. The first big question is simple: is it constant? We call it the cosmological constant, but that's an assumption. Our measurements have a margin of error, and that sliver of uncertainty is where all the drama is. It's the space between a quiet freeze and a violent rip. Every new supernova we measure, every map of galaxy clustering, tries to shrink that error bar, to see if the number W has stayed the same for billions of years, or if it's begun to change. That leads to the second unknown: could it be phantom energy? The data from current surveys likes the simple constant, but it doesn't rule out the phantom. The possibility is still there. However faint, that dark energy's push is getting stronger over time. It's a hypothesis that refuses to be dismissed, a ghost in the data. To answer this, we need more than snapshots. We need a movie of the universe's expansion, with a precision we've never had before. Then there's the quantum problem. How does this smooth, repulsive field interact with the quantum world? Our two most successful theories, quantum mechanics and general relativity, give wildly different answers about the energy of empty space. This isn't a small discrepancy. It's the largest mismatch in all of science. Bridging that gap requires a theory of quantum gravity, a framework for both space-time and the particles on it. Until we have that, dark energy is just a placeholder, a label for an effect we don't understand. This brings us to the most baffling puzzle. Why is the value of dark energy so incredibly small? If it were just a bit larger, the universe would have blown itself apart before stars could form. If it were zero, the cosmos would look very different. Its precise, tiny value seems fine-tuned, almost as if set to allow for a long history, the kind that produced us. Is this a cosmic coincidence, a selection effect in a vast multiverse, or a clue to a deeper symmetry? We don't know. These aren't failures of science, they're its frontiers. Each unanswered question is a beacon, guiding the next explorers. The James Webb Space Telescope, looking at the earliest galaxies, will trace how structure formed when dark energy's influence was just beginning. Ground-based observatories like the Vera C. Rubin Observatory will scan the sky, collecting billions of data points to tighten the constraints on dark energy's evolution, and theorists around the world are working on new ideas. Modified gravity, extra dimensions, trying to build the tools to make sense of it. This honest admission of uncertainty is where the true wonder lies. It means the story of our universe's fate isn't a foregone conclusion. The final chapter isn't written yet. The next great discovery from a telescope or a chalkboard could reveal a twist. It could make our visions of a big rip or a heat death obsolete. The cosmos holds its secrets close, and the greatest thrill is realizing we're living in the era where we're finally asking the right questions. The search itself is the legacy, a testament to a curious species looking up at the stars, daring to chart the journey from the first moment to the last. The universe's final chapter isn't written. We started with that first discovery, the cosmos accelerating, that led to the idea of the Big Rip, a timeline where everything comes apart. Galaxies first, then solar systems, planets, until finally atoms themselves. Silent, disintegrated, it all hinges on dark energy, on whether it has this phantom nature. That's the condition. It's speculative, but it's a testament to the forces we can't see shaping everything, and to how much we don't yet understand. The scale is immense. The rules can feel hostile to our brief human moment, but we look anyway, we measure, we build stories from the faintest light. Trying to comprehend an end like this, it ends up teaching you about beginnings, about our own fleeting place in it. Richard Feynman said the universe isn't obliged to make sense to us. But our curiosity, that's an obligation we choose. It's how we map the darkness, find constellations in the void. The quest doesn't stop here, there are more secrets. In deep space, in gravitational waves, in equations no one's written yet, your thoughts on this, on any of the puzzles, they're part of that conversation. The search for knowledge, that story doesn't end.